Hello, grade 11s. Welcome back to the channel, Science Therapy, hosted by the one and only science therapist, Uabudewa Sos Ugobela Wemets. And without any further ado, let's look at this question that we have here. Okay, so we have ammonia, NH3, and hydrochlorous acid, HOCl, are both examples of covalent compounds. Then 2.1.1 says define the term bonding pair. And then let's run quickly to that one. You say a bonding pair are two electrons shared between two atoms in a covalent bond. So note that definition there. That's how they expect you to define that for 2 marks. Then 2.1.3 says draw a Lewis structure for the following molecules. Now, watching all my videos, you can almost see the trend when it comes to this question. It's your definition, then we go to drawing the Lewis structures, then we go to answer all those questions about the bonding pairs and the lone pairs, right? So note that trend there, and then always keep to that. Now, if we are to draw this one, we have NH3. And then to make one of this essential atom, we know that the NH3 ammonia is formed out of one atom of nitrogen and 3 atoms of hydrogen. Now the nitrogen is obviously the more electronegative one, so it has to be the central atom, and also the fact that it is only one of that. So that's nitrogen, but the nitrogen is in group number 15. Looking at our Roman figure, we can see that it has 5 valence electrons. So this is how we're going to go about it. 1, 2, 3, 4, 5, right? And then at this point, we are only left with these ones here. So what we are going to do is we're now going to fill in our hydrogens right there. So hydrogen here, hydrogen, hydrogen. So we have 3 hydrogen atoms, and then they come with their 1 valence electron there, and then they form a bonding pair. So this is what we call a bonding pair. So in order for you to establish a bonding pair, 1 electron must come from one atom, and another electron must come from the other atom, unless we are forming a dative covalent bond. That's where you have 2 electrons coming from only 1 atom. Right. Then for B now, so this was for A. For B, which one are we making? So here we can see that we have 3 different atoms. So it's a battle of which one do we make the central atom here. But then you can easily just see it from here. You can just make oxygen the central atom. So we have our oxygen like this. And then there we go. We have 1, 2, 3, 4, right? And then with this one, what we normally do with this one is that we just form our lone pairs here, so that we are able to put the hydrogen and the chlorine this side here. So we have the hydrogen, and then we have the chlorine here. And then this one is coming with its 1 valence electron, but then the chlorine, remember chlorine is in group number 17, meaning it has 7 valence electrons. So that's 1, 2, 3, 4, 5, 6, 7. Right. Now it is not necessary for you to have all those different colors to indicate. It's just a matter of me having to show you that the chlorine came with its 7 electrons, and then the oxygen with 6, and the hydrogen with only 1. So the bonding pairs are here. The bonding pairs on the central atom, there are 2 bonding pairs, and then there are 2 lone pairs, right? So, okay, now let's move. 2.1.3, it's saying write down the number of bonding pairs in NH3. So I'm not going to erase these ones so that we are able to answer those questions based on something that we can see. Now they're asking number of bonding pairs in NH3. As we can see here, how many bonding pairs? It's 1, 2, and then 3. So we're going to give them the solution. We have 3. So for 2.1.3a, that's 3. And then for B, they're asking number of lone pairs on the oxygen atom in HOCl. as we spoke about it. So this is the number of the lone pairs. We have a lone pair here and a lone pair there. So how many lone pairs do we have in total? We have 2 lone pairs, right? So that's 2. And then C, what is the shape of the ammonia molecule? The shape of that one, we call it the trigonal pyramidal. Trigonal pyramidal, right? So trigonal pyramidal. So that goes to you having to study the shapes, study those molecular geometries, all the way from your trigonal planar, your trigonal pyramidal, trigonal bipyramidal, your tetrahedral shape, your linear, your bent or angular shape. It all comes in you having to know all those things there, right? Then let's now proceed to 2.1.4. Which bond, is it N2H or O2H, is more polar? Give a reason for the answer. So which one is more polar? Now, obviously, for that one, we would have to calculate so that we know the difference. So what calculation are we going to use here? Is the electronegativity difference, right? And then if we are to start with this one, we can say the electronegative value of the nitrogen minus the negative value of the hydrogen, right? And then having to calculate that one, we have 3 minus 2.1, because remember with nitrogen, that's 3.0 there. And then if we say 3 minus 2.1, we end up with 0.9. And then if we do En 4, so let's indicate this one here, it's for N2H. And then En, this is En of oxygen minus En of hydrogen. So always you'll have to take the electronegative value that is larger minus the one that is smaller, right? So because we know that oxygen is more electronegative than the hydrogen, that means it's the electronegative value of oxygen minus the electronegative value of hydrogen. But then for oxygen, remember we have looking at our periodic table, for oxygen, we can see that we have 3.5. So that means it's 3.5 minus 2.1. Now 3.5 minus 2.1, this is 1.4. Now from the calculation, it is now easier to tell which one is more polar. Remember, the greater this electronegativity value, that means it is more polar. So this one has to be more polar, right? This one is more polar. So this one is a weak polar covalent bond, but this one is a strong polar covalent bond. So in other words, our solution is, therefore, it's the O2H bond, right? It's the O2H bond. So the explanation really comes in the form of just calculating this. So they will just have to give you a mark for calculating this electronegative values of the two bonds, and then having to conclude that the O2H is obviously the more polar bond. So let's now proceed to 2.1.5. It says, write down the type of intermolecular forces present in both ammonia and hydrochlorous acid. So now they're touching on those intermolecular forces. And then now we can see one common thing about this is that we can see that the hydrogen here is bonded to a nitrogen, but then the hydrogen here is bonded to an oxygen. You will remember that we have what we call Hoff-North, like this. And then we normally say if a hydrogen is either bonded to an oxygen, a fluorine, or a nitrogen, we call these bonds the hydrogen bonds, right? We call this the hydrogen bonds. So in A, NH3, we can say that the hydrogen is bonded to a nitrogen. But then in B, the hydrogen is bonded to an oxygen. So both these molecules, they have what? The hydrogen bonds. So for 2.1.5, we're going to say this is the hydrogen bonds, right? So always note that, remember Hoff-North, if a hydrogen is either bonded to an oxygen, a fluorine, or a nitrogen, then the type of intermolecular forces there are the hydrogen bonds. Then, okay, let's now proceed to 2.1.6. They are saying when ammonia dissolves in water, the ammonium ion is formed. What type of bond forms between the ammonium molecule and the hydrogen ion? So again, they're coming with this one. I always made you note that if ever they're asking you about the ammonia reacting with a hydrogen ion, always note that that type of bond is called the dative covalent bond. So you have two of them that they're going to ask. It's either it will be this one and that one forming ammonium ion, or if it is not this one that they're going to ask you about, it's obviously going to be the H2O reacting with the hydrogen ion to form the hydronium ion. So two of this, you'll be asked about these ones, and then you always have to note that this is dative covalent bond. So always, if they ever come to you with any of this and then they ask you what type of bond is occurring there, do not hesitate. It is dative covalent bond. Right. Then let's now move. We have 2.2. The graph of potential energy versus distance between the nuclei of two oxygen atoms during bond formation is shown below. Now, in 2.2.1, they're saying define the term bond energy, right? So what is bond energy? We say this is the energy. So for 2.2.1, we say this is the energy needed to break 1 mole of a compound's molecule into separate atoms. So that's how you define bond energy. You say it's the energy needed to break 1 mole of a compound's molecule into separate atoms. So that's how they expect you to define that one. Then for 2.2.2, they say which curve A or B represents the formation of the double bond between oxygen atoms. Briefly explain the answer. Right. So we have two there. We have two graphs here, graph A and graph B. Right. Now they're saying which one represents where you have to break the double bonds. Now, one thing we know that double bonds, they obviously have a stronger bond strength, and therefore they will require a lot of bond energy, right? So greater bond strength, that means greater bond energy required. So obviously, looking at this one, we have to check which one has a greater bond energy. Now, bond energy, we know that it is all the way from the x-axis there to where we find the peak there. So if we have to compare the bond energy of graph A and the bond energy of graph B, we can see that this one has a greater length than that one. So the one for A, graph A, obviously it's indicating that this one has a higher bond energy, but this one has a lower bond energy. So in order to break a double bond, obviously we need a higher bond energy. So it has to be A. So our answer is A. And then we say when the bond order increases, bond order, we mean it's now moving from single bond to double bond. So when the bond order is either it's a single bond, double bond, or triple bond. So when the bond order increases, we say the bond length decreases. The bond length decreases. Right. So because again, we know the relationship between bond order and bond length is inversely proportional. So as we are increasing with bond order, the bond length decreases. Right. And then obviously, we then expect the bond energy increases. Right. we then expect the bond energy to increase, this is what we are speaking about here. So we know that bond order is directly proportional to bond NH, right? So one with a greater bond order will need a higher bond NH. But then bond length, again, we know that it is inversely proportional to what? To bond NH. So if we have a decrease in bond length, then we have an increase in bond NH. So it all boils down to those relationships there. It all boils down to those relationships. So when the bond order increases, the bond length decreases. And then therefore, if the bond length decreases, then the bond energy increases. If you can check, this is all based on these relationships here. So make sure that you note those relationships into your book so that next time you are able to answer such questions. Right. Then now, in 2.2.3, they're saying write down the bond length, right? Write down the bond length of the bond represented by curve B, right? So represented by curve B. Now, to indicate the bond length, this is what you do. You go for the value that is just directly to the peak there. And then you just go like this. So this distance here from this point of origin all the way going to the x-axis up until the point that is directly to the peak will represent what we call the bond length always, right? So this is your bond length. Now you can even see what we talked about. Because this one is a higher bond energy, look at its bond length. It has a smaller bond length. But this one, because it has a lower bond energy, look at its bond length. It has a greater bond length, which is telling you that bond length and bond energy are inversely proportional. The greater the bond length, the smaller the bond energy. But then the smaller the bond length, the greater the bond energy. So again, pay attention to that relationship. But then, okay, we are not on that. Remember, what we are being asked about here is this bond length here. So what is the bond length? We have 148. And then how do we give the SI unit? The SI unit is always given here, picometers, right? And then 2.2.3, that means our solution that's supposed to be 148 picometers, right? That's how you go about answering those ones. So it's not PM as the time, it's picometers. So with all that being said, guys, please press the thumbs up button if you've enjoyed the lesson. And then if you've been watching the videos and haven't subscribed yet, please hit that subscribe button. But most importantly, please share the link with your friends and classmates so that they may also find assistance. Remember, do not be selfish. We are winning as a team.